Now that we've learned about sets and taken a good look at set membership, we can introduce two ways of comparing sets in terms of the elements that they have in common. Let's suppose we have a set consisting of the names of all the students enrolled in a discrete math class. The professor for that class might need to send a message out, not to the entire class, but just to the first-year students to remind them to go see their advisors. The group of interest is a portion, but not all, of the names in the class. Every person in that group is in the class, but we only want to send the message to them, not to everyone. In that case, what we are using is called a subset of the set of all names of students in the class. This group of first-year students isn't the only subset of the class. We could send messages to all the graduating seniors, or all the students whose first names begin with a G, or all the students who were sitting together at a particular table on Monday. Generally speaking, if A and B are sets, then A is a subset of B if every element of A is also an element of B. We use this notation, which looks a little like the less than or equal to sign, except it's rounded, to indicate that A is a subset of B. So for example, the set 1, 2, 3 is a subset of the set 1, 2, 3, 4, and so is the set 2, 4. Even the set 1, 2, 3, 4 itself is a subset of 1, 2, 3, 4 because every element of the set on the left is an element of the set on the right. This means that every set is a subset of itself. Another example would be the natural numbers, which are a subset of the integers because every natural number is an integer, and the integers are a subset of the real numbers because every integer can be located on the number line. That chain of subset relations means that the natural numbers are a subset of the real numbers too. The real numbers can have finite subsets as well. For example, the set pi square root of 2 is a two-element subset of the real numbers. On the other hand, the set 1, 5 is not a subset of 1, 2, 3, 4 because not every element in 1, 5 is an element of 1, 2, 3, 4. We can see that 5, although it's an element of 1, 5, is not an element of 1, 2, 3, 4. Now you try it. Here's a set M-A-T-H-E-I-C-S, the different letters used in the word mathematics. Which of the following sets are subsets of this? Take a moment and identify them, then come back. Here are your correct answers. The first two sets, A and AM, are subsets because every element in each one is also an element in the set we started with. AG is not because the letter G is not found in the original set. And the last one is the same as the original set, and we've already explained that every set is a subset of itself. You might have noticed that we can think about subsets using quantifiers, which we learned in Module 2. The definition of subset says that A is a subset of B if every element of A is also an element of B. In quantifier language, that would say that for all x in A, x is in B. This helps us think about what it means for a set not to be a subset of something else. The negation of for all x in A, x is in B is the statement there exists an x in A such that x is not in B. That's why the set AG was not a subset of MATHEICS, because there exists an element in AG, namely the letter G, that is not in the set MATHEICS. Here's another question for you. Is the empty set a subset of MATHEICS? Pause the video and think about this, and then come back when you've decided yes or no. This one takes some careful reasoning. We can think of subsets in terms of conditional statements too. The statement for all x in A, x is in B can be rephrased as the conditional statement if x is in A, then x is in B. So look at the proposition, the empty set is a subset of MATHEICS. As a conditional statement, this would say if x is in the empty set, then x is in MATHEICS. Well, the empty set is empty, so the hypothesis of that statement, x is in the empty set, is always false. And when the hypothesis of a conditional statement is false, the conditional statement itself is true. So believe it or not, if X is in the empty set, then X is in MATHEICS is a true statement, and therefore the empty set is a subset of this set. In fact, by this reasoning, the empty set is a subset of every set. In addition to subset relations, we can talk about whether two sets are equal. Two sets are equal if they contain exactly the same elements, like the set 1, 2, 3 and the set 3, 2, 1. These are equal sets because they have the same elements. The ordering doesn't make them different. But it can be hard to tell sometimes if two sets have the same elements. For example, is the set 1, negative 1 equal to the set of all x in the real numbers such that x squared equals 1? One is a finite set, and the other is in set builder notation. It's hard to tell if these two sets have the same elements just by looking. So we will say that the set A and the set B are equal if A is a subset of B and B is a subset of A. This makes it a little easier to determine if two sets are equal to each other. For example, in this case, A equals the set 1, negative 1 is equal to the set B of all x in the real numbers such that x squared is equal to 1. And here's an explanation. First, A is a subset of B because if x is in A, then x is either 1 or negative 1. And in each of those cases, x squared is equal to 1. Therefore, x passes the filter given by the predicate in that second set, and that makes x belong to B. And that makes A a subset of B. Likewise, if y is in B, then y squared is 1. And a little algebra shows that y squared minus 1 is 0, so y plus 1 times y minus 1 is equal to 0, which means that either y is 1 or y is negative 1. Therefore, the y that was in B is also in A. That makes B a subset of A. Since A and B are now subsets of each other, that means that they are equal. So in this video, you learned what it means for a set to be a subset of another set, and what it means for two sets to be equal. Those are basic tools for comparing sets. See you in the next video.